Okay, excellent. Right, very good. Yeah, super. So let's begin with a tutorial that Sam and I have put together with a bit of help from Jerry as well. So we just had a few things that we wanted to say before we jumped in and started it. The first one was really to strongly encourage everybody to join the Julia Slack community. I mean, I think if you want to use Julia, this is one of the places that you definitely want to be. So if you follow that link from the slide, you'll be able to do that. And then we have a Julia Hep channel.
Graeme, excuse me, I think you're not sharing the slides.
I am not sharing the slides. Okay.
I will say from my view remotely here in Glasgow, what I can see, Graeme, is you talking and some slides that are hard to see because of the light bounds. So
Yep. So now I have the issue of having a gazillion windows open and not being sure where the heck things are. Right. I mean, to be fair, we weren't scheduled to start this until 1:15, so I still feel that I'm in my like free time here. Yeah.
oh yeah, we've got a whole 10 minutes to debug, Graeme. I mean, this is fine. We should...
Right, and I will not join the audio. Yes, got it. Fine, thank you. Let's go away, share screen. Right, let's try that. Desktop share. Okay. Does that look better?
Yeah, I see stuff. That is good.
Perfect. Thanks.
Right, floating meeting controls. Great. Okay, yes, very good. Yes. Slight technical glitch. It always happens. What do I do? Get rid of, try and make this a lot smaller as well. Yes, very good. So yeah, please join Julia Slack. And we have a Julia Hep channel there. And that's the place that we're going to use. We probably won't have time. Of course, we don't have that much time to get through an introduction to Julia and also all of the exercises. So I would anticipate that people might want to try these later on in their own time. And then if you get stuck or you have questions, just ask a question on the Julia Hep channel there. So Sam and I are going to share the presentation of the material. This is a new tutorial. Well, that's not really completely fair. This is a tutorial where we have harvested material from clever people from many other places, as you always do with these kind of things. So our thanks to everyone that's written any Julia tutorial ever, because we probably read it when we were doing this. So it's very fresh. That's great. But of course, there might be some rough edges as well. So the link there is to the GitHub repository. So please just raise an issue if you notice something that needs to get fixed, or you think that there was something which was really important that we missed out. We've written the tutorial as a series of notebooks, so you can run them yourself. You can either just clone them directly onto your machine, or thanks to Jerry, we have a link set up that you can run it on the Iris Hep binder, as long as you can get through their authentication. But, you know, I think for most people, you should have something that works. And it's also kind of wired in to do a set of web pages from the tutorial, which is how I'll do the presentation this morning. And that version is available on juliahep.org. So you can follow that link and you'll find the tutorial there. So our kind of rough timetable for how we're going to do this is, well, I'm just giving you this slide now. So that's early, that's good. We'll then have 40 minutes on sort of very introductory bootstrapping, how do I get going with Julia material. We then have half an hour for people to try one of the exercises that actually gets people hands-on doing something. Then we'll have some coffee because we'll need it by then for sure. And then we'll just talk about, I mean, there's so many things that you could, interesting things that you could learn about in Julia, so many things that you will learn about, but we'll go through plots and data frames as being sort of two of the most interesting and popular things which are in the Julia ecosystem, and then we have a few exercises that people can try to finish off that. Okay, now the other thing that we have is a couple of very lightweight, kind of like not very serious quizzes, which we're going to do. So let's try and get started with that. Oh, why is this? How do I get out of full screen now? Good grief. Okay, finally, yes. All right. So let me try and find where that is. And we'll attempt to see if this works. Okay, so if you follow that link there, then you should be able to find a question on Mentimeter.
I will say, we will be a little bit more terrified if everyone keeps on clicking the allot button, given this is an introduction to Julia. We'll just have you give it if everyone ticks that.
Fine. Here we go. So we just wait for the answers to come in there. Yeah, this was just to give us some kind of idea of what the audience was like here. Yeah. Okay. It's coming in. All right. We now face the terrifying prospect of giving an introduction to Julia tutorial to a bunch of experts. Great. Well, hopefully other people will find the tutorial interesting later on. Okay, so some people like owning up to the fact that they're Julia curious rather than experienced so far. Okay, very good. And then the other thing that I was sort of quite interested to ask people was, do you actually have Julia installed on your machine? So just to know how much time we might want to spend on installing it. Okay, it's great. Everybody's got Julia already. Fantastic. Well, this is really good because this means I can completely skip the bit of the tutorial, which is about how to install Julia. And I think it proves once again that this is, it's quite, okay, one person needs to know that. But, you can use the binder instance or you can install it yourself. Very good. Okay, let's take a break from that just now. If I can get this thing to come out of full screen mode. Oh, yeah, this is a... Right, very good. Okay, so let's then actually jump into the tutorial and we'll go, hey, full screen. All right. Okay. Sorry, let's get rid of this rubbish again. Okay, right. Is that about visible for people in terms of it not being too small? Please shout out if... Let's try going one back.
Remotely, it's fine. So you probably want to ask people in the auditorium, Graeme.
Right. Okay, good. Let's go on. Let's go with this then. Okay, grand. So, yeah, why Julia? Julia is a relatively young programming language, but I think what I'm very excited about with Julia is that it's really a programming language that has absolutely been targeted at scientific computational workloads. So in many respects, it's been inspired by key languages for scientific computation in the past, like Fortran and MATLAB, but it's been engineered with a lot of the things that we've learned about programming languages and environments over the years. So it really does have the look, the feel of a really modern dynamic language, but with amazing sort of good integration and features for scientific programming. So I think if you wanted to sort of put your finger on a language that people might have previously met that kind of feels a little bit like Julia, I think we would often pick Python. as being that one in terms of its ease of use and the way that you can easily interact with it. But what's great about Julia is that, like I say, it's been built from the ground up for highly optimized scientific computing, whereas in Python, you will run into the problem that the language itself is rather slow. And if you use third-party libraries to try and get around that, such things like NumPy and Numba, you often actually have to sacrifice a lot of the convenience of the language to be able to get access to those higher performance libraries. And even then, honestly, probably you really don't meet the kind of performance that you can get out of C++, and other like compiled languages, whereas Julia actually can. Okay, so some of Julia's key properties, I mean, high performance, as I just mentioned. You know, you will usually approach the performance of code that's written in C. Sometimes you even get a little bit faster as well, so it certainly runs fast. It's a modern language, so you have full support for Unicode, which actually turns out to be incredibly nice when you're picking variable names. And you have LaTeX markup supported as well. Natural mathematical symbols just exist. So this is convenience stuff, but it's very nice convenience stuff. You have first-class support for notebooks. So this is the Ju in the Jupyter name, because it's Jupyter, Python, and R is the Jupyter. A generic programming model, which is incredibly powerful using multiple dispatch with function method chaining and other modern paradigms. And we'll explore that a little bit in the tutorial. And I think you'll start to appreciate just how good this is from a programming point of view. It's a dynamically typed language, but the typing system in Julia is built very deeply into the language. And this allows it to be both dynamically typed and generic, easy to use, but to generate code, which is going to run extremely fast as well. And one of the things that I like as well about Julia is that it has a really great package manager built into it as well. So, you know, things are not so terrible in the Python ecosystem because you have pip, conda, and mamba, and so things like that. But when I have to go back to C++ and it's like, oh yeah, right, now I need this version of a JSON library. Now I need this version of HepMC. Now I need to compile FastJet and link them against all of that. Just like, oh, this is quite painful. So yeah, these kind of things just make Julia, for me anyway, a really fun language to program in. So I'm really happy to give this introduction to you here. Okay, so let's just start off by looking at a little bit of Julia code. So this is like not going to be super surprising to anyone. In fact, I think it's designed to be reassuring more than anything else, that if you have experience with programming languages, I'm sure you can read that and realize what it does. Oh, like we're just going to examine two variables and decide whether one is greater than the other, and we can run that function and print the results, and it all looks good. So y is greater than x in the first case, and x is greater than y in the second case. Just one subtlety that we want to point out here, which is that all expressions in Julia return a value. And so here we're using the fact that the last expression which is evaluated is this string statement here. So this becomes automatically the return value of the function inside of Julia. So this is actually a really nice and very commonly used feature inside of Julia, that you just state what you want to return on the last executed line of a function. You can, of course, if you want to, you can put in an explicit return statement. So there's an example which is shown there, but it's not really necessary, and it's just sort of much more natural in Julia to not bother about that. Okay, just a little important thing to realize about Julia, of course, is that it has a JIT, so just-in-time compiler, or just ahead of time is probably the more accurate way of saying it. So essentially, Julia, what it's going to do is the first time that it meets a block of code, it's going to look at that code and it's going to say, okay, right, now I need to compile this, guys, and off it goes, and it generates the appropriate machine code to execute the function. which does mean that the first time that you execute a code block in Julia, it's going to be slower because at that point, it needs to be compiled. And we just give a little example of that now. So there's this little bit of code, I think, due to Jerry, which is here. It doesn't really matter what it does. I think the important thing here is just to state that when you use this nice little time macro, by the way, that's a very handy thing for working out how much time a particular piece of Julia code takes to execute. The important bit here is that you can see that this code took 99% of the time was all the compilation time for the code. So that's just something to be aware of in Julia, is that sometimes it takes a little bit of time to execute your code for the first time, but after that, it will speed up a lot. So yeah, so this goes from, yeah, it speeds up by factors of, I don't know, 1,000 or something there. So the second time that you call the code, it's much, much faster. So then it runs really quickly. So that's one of Julia's features, which you should definitely be aware of. So that's a kind of, you know, basic first look at the language. The next part of the tutorial is on installing and running Julia. Honestly, I think I'm going to skip this because I think most people have this up and running. If you don't, just have a quick look at this and it just points you to the right places to get Julia up and running. And then there are some examples here of how you can start the REPL inside of Julia. This is like IPython if you haven't used the Julia version, how you can run in notebooks and how you can run with scripts as well. And then as a bonus, yeah.
Sorry to interrupt you. Oh yeah, you're there. I just wanted to tell you that maybe we should mention Julia because I know a lot of people use Julia, but don't really know that Julia is really cool.
Right. Yes. And I think if you don't know that Julia exists, you would kind of go through the normal way of installing Julia, which is great because it's very robust and it works really easily. But actually, Julia is also very robust and it works and it offers you quite a lot more features. So yeah, I think that would be the way that I would genuinely recommend people to install Julia if you're going to do anything more serious with the language. Okay, but skipping over that relatively quickly, let's go on to look at a little bit of Julia syntax. This is your kind of survival guide to Julia. So of course, it's a programming language. That means Julia has variables. A variable is basically just a name which is bound to a value. And I give you 3 examples of variables there. Assignment to a variable is done with equals, like all programming languages since the dawn of time, basically. So there's no surprises which are there. There's maybe one interesting little thing that you might notice is that when we execute these 3 statements here in a notebook, we actually do get an output, and it's this thing that everything produces a value inside of Julia, and in this case, it's just the value of the assignment. And Julia will print that when you're running in a notebook or the REPL mode for Julia. Sometimes if the thing that you're evaluating has a very big representation, you don't want that, in which case just add a semicolon onto the end of the line and it will suppress that output. So if I now set just a delta2 variable but put a semicolon, there's no output at all. Okay, so great, we have variables. Excellent, it's good to know. Little bit about operators. The operators work basically as you would expect, so they're kind of all the same commonly across the vast majority of programming languages. The only ones that we wanted to point out here are the ones that might be slightly different from the ones that you've previously met, which is that the hat is the power operator. An actual division symbol represents an integer division. Percentage represents remainder. Well, that one is used in other languages, but the integer divide, it just looks really nice. I think the fact that you have a proper mathematical symbol. So you just type \div at the REPL or in your editor, and you should get a division symbol, which is there. So yeah, hat for exponentiation, not a double star. And yeah, you can just execute a few things like that. So 2 to the power of 10 plus 33 integer divided by 10 So you get 1,024 plus 3, so you get 1,027. So all of those statements execute just as you would expect. Okay. Bitwise operators exist as well, and they're supported for all the primitive types. So you have a bitwise NOT, AND, OR, and an XOR as well. So you can play about with these as well. I just give a few examples here of some integer values that you can calculate the bitwise OR and AND of there. And later on in this session, Sam will introduce the vectorized or broadcast operations, which are an amazingly nice feature of Julia. Of course, once you've set a variable, you can reset it to something else because almost everything is mutable here. And Julia supports the usual range of updating operators that you would have in things like, you know, the same as Python, so plus equals, minus equals, so on and so forth. So it's very simple to double the value of a variable. Many times we need to test the values of variables against certain criteria. So you would have the usual operators for testing the values of variables, so equals, greater than, less than, and greater than, less than, equals. They're going to return you a special type of variable, which you won't be that astonished by in a modern language, which is a Boolean type, and a Boolean type can be true or false, obviously, as well. So A is greater than 8, yep, that's true. A is less than our delta 2 variable, nope, that's false. And if you want to negate a Boolean, you just put an exclamation mark in front of it. So not true turns out to be false. Okay, there you go. So that's good. You will also see inside of Julia code a triple equals sign. And this is a nice operator in Julia which tests whether two objects are actually the same object. Okay? That's a stricter test than do they have the same value. And I just show an example of that here. We set up a tiny little vector A and B, which have the same content, the numbers 1 and 2. And we set a C equal to A. Now, does A triple equals B? The answer is no, because although they have the same content and they would pass a double equals test, they're not the same object intrinsically, so that is false. But A and C are set to one another, which means that the triple equals evaluates to true, which would mean that if you changed the value of C and then printed A, you would see the changes in A as well, because they are actually the same object. Okay, and then a nice little feature is that Julia allows you to chain comparisons, so you can have a nice chain there of numerical comparisons, and that's going to evaluate to true. Okay, so we have variables. All of the variables actually have types, and as you would expect for a language for scientific computation, you have integers and floats, all with varying bit widths as well. So just a floating point number, at least on my machine, is definitely a float 64. You can explicitly state what type of variable you would want. So here for I set it to being an unsigned integer, which actually Julia always prints in hex notation, because that's usually the reason that you want an unsigned integer, is because it's a mask for something. And then if we examine the type of I, it tells us, yep, it's an unsigned integer, 64 bits. Okay? If you want to mix precision, mix types in arithmetic in Julia, generally that's safe and it will just work as you expect. Julia does a thing which is called promoting variables, whereas you sort of always get them up to the highest common type, and then you do the operation there. So if I multiply my float by my unsigned integer, then I get a float back, because that's the promoted type for an integer, and a float is to take everything to floats. So generally, Julia will do this if it's safe, but it will throw an error if it can't make a conversion safely. So this is a nice feature of the language, is that generally it will not just silently get things wrong. If I try and cast my long unsigned integer into a small integer, and in 16 I get an inexact error. I can't do that because the number that you've given me just does not fit into an int 16. So Grant, that's Julia generally handles numeric types in the way that you would want and expect. Okay. Now you don't need to specify types for variables in Julia. Unlike C++, by default, it works kind of like Python. You can just freely assign any type to any variable at any point in time. There are some times where you do want to specify the type. And the way you do that in Julia is you add a : : type to the end of the variable, and it tells Julia, hey, this variable is going to hold this type, and you shouldn't put anything else into it at all. So if we tell Julia in this example here, the integer value is going to be an int 64, and then we assign a float to it and to ask Julia what it is, we actually have an integer value still. Now that was safe to do because 2 can be represented by an integer exactly. So if we try and do something like integer value equals 2.5, then again, Julia says, I'm not so sure about that. Is that what you really meant? And we get an inexact error, which is thrown because we were trying to implicitly convert a float into an integer in a way that can't be done safely because we're losing precision. Now, let me touch on something interesting for types in Julia, which is, so this is really just a very high level piece of information, but it's important to have this in mind as you learn more about the language, which is that Julia's types are arranged in a hierarchy. So they go from more general types at the top of the hierarchy tree down to specific types at the bottom, or concrete types at the bottom as well. So you can see that at the very top of the Julia type hierarchy, you have an any, and any represents literally any object in Julia is of type any. And then some of the more important types are given at the second level of the tree there, so numbers, strings, and arrays. If we follow the numbers down a little bit further, you have real numbers. Real numbers can be integers or floats. Integers can be signed or unsigned. And then at the very bottom, we get down to some of the concrete integer types, 64-bit and 32-bit integers there. Now, there's an important thing about this diagram that you should know, which is that all of the boxes that have dashes around them are what are called abstract types, and the ones which have solid lines around them are called concrete types. Concrete types have to be leaves of the tree, right? They don't work as abstract types. You cannot instantiate a variable with an abstract type. It has to be a real type. So an actual number variable in Julia has to be a specific integer or floating point type or something like that. But the real value of this is that when we're defining a function, we can say what type of variables this function will accept, and there we can use the abstract types. So I can define a function and I can say, this function is got to take numbers, right? But I'm not going to tell you which numbers you're going to get. That doesn't matter. Could be integers, they could be floats, they could be rationals, but you can just sort that out at the time. But if somebody tries to pass a string to this function, that is no good, and you should not handle that. So this is when you start to work with the Julia type system, you will start to realize just how powerful and useful it actually is. Okay. But that's all we'll say about it now. Let's just mention a few of the other variable types that we have inside of Julia. So complex numbers are built into the language. So IM is used as the imaginary number constant, but they work just as you would expect. And also rational numbers are built in as well. So that's a double slash to define a rational. So you have 2/3 and 1/4. And when you multiply them together, you get another rational number actually comes out of it. So Julia is very powerful for doing exact rational arithmetic. Now, strings must exist as well in the language. So they're defined by double quotes in general, or by triple quotes, right? Which allows the use of unescaped double quotes inside the string, and that's much nicer than using backslashes. And triple quoted strings can also be split across multiple lines, and that's a really nice feature as well. So yeah, things are very easy to use with strings inside of Julia. The only maybe the thing that is maybe slightly surprising to people is that you concatenate strings in Julia using the multiplication operator, a star, rather than the plus. And the reason that this is done is because multiplication is not commutative, right? So hello world is not the same as world hello. Therefore, a plus is considered to be an inappropriate symbol for concatenation. It's a little gotcha because in most other languages, a plus is used. Strings are all Unicode inside of Julia, which is very useful and as things should be inside a modern language. But you do just have to be a little bit careful to use indexing inside of strings, because sometimes you can be sort of inside a Unicode character when you take an index and then you don't get a valid character back. But generally that shouldn't trouble you too much. And there we go. So just some example of how to use Unicode inside of your strings. That's all fine. And one of the loveliest things that Julia has in its string library is interpolation. So if you use a dollar and parentheses inside of a string, then the expression which is inside the parentheses is evaluated and the result is put into the string. You only need to use the parentheses if it's sorry, you don't need to use the parentheses if it's a valid variable identifier. You can miss it out. So I can say m squared is m squared, and the string that comes out is exactly the string that I would want to see, where I actually see the imaginary number and its square. Okay. Moving very quickly on through the types, we have in Julia arrays, dictionaries, and other composite types as well. So arrays are just set up using square brackets inside of Julia. They can be arrays of any type inside of Julia. So they can be as flexible as Python lists. So they can hold objects which are of completely different types, or they can be very specific and they can hold, only a very concrete numerical type. The difference is very important because Julia can strongly optimize arrays where the type is known in the particular array, whereas it can't optimize arrays of any, so that code would run a lot slower. There's also array comprehensions as well. So little expressions like this will give you back exactly the array that you were expecting. One-dimensional arrays we also call vectors inside of Julia, but the multi-dimensional arrays, and I think arrays in general, are interesting in Julia because they're first-class types. They're not an add-on to the library. So things like arithmetic operations on arrays inside of Julia do the mathematical thing that you would expect of arrays. Okay, what else should we say here? Yes, that means that when you're indexing arrays, as well, it's a single array index which is used to indicate the index that we want to identify. So here, the example is that we're just pulling out the top left value of the identity matrix there, just using a 1,1 specifier there. So there's lots of ways that you can create arrays efficiently. So just see the documentation. Dictionaries are very useful as well. These are I think they're called hash maps or associative arrays in C++. In Python, they're called dictionaries. The syntax is just that you use this equals and then arrow, greater than sign, to assign keys to values. So a very simple example here is we set up a dictionary which maps one string to another string, and in this case we're letting us understand what sounds farmyard animals make as well. Again, like the arrays, dictionaries are specialized on the type of the key and the value as well. So in this case we have a string and a string, so that's what we're mapping one to another. Julia has tuples and sets. They work exactly the same as they do in Python, so I think we don't need to really explain them here. Julia also has user types. Okay? So these are custom composite types that you have. These are called structs inside the language. And the struct definition, like many of the other constructs inside of Julia, starts with the keyword struct and it ends with end. So you have a structure here which just has two float 64 variables. Just one thing to note is that structs are immutable in Julia by default, so you can't update their elements, which allows optimizations to be made. If you want to have a mutable struct, then you just need to put the keyword mutable in front of the structure, which is there. So great. That's kind of the introduction to operators and variables inside of Julia. And then the last part that I will cover before we flip over to Sam is a little bit about functions and control flow. So functions inside of Julia are just introduced with the keyword function and then an end at the end of it. You give a name to the function and then you say what kind of arguments the function will take. Here we simply define a function that multiplies its two arguments. And you'll notice that we didn't specify any types on this function, so we haven't told Julia what it should do there. That means in principle, Julia can accept any types into that function and it will try its best to handle them. So we can then just take an example that we multiply two integers together and it works. We multiply two complex numbers together and it works. We multiply two strings together and it works, because remember that the star operator for strings just means concatenation. So we get all three versions of the function. These functions will all stay really fast inside of Julia because of this specific compilation that it does for the concrete types and the multiple dispatch that Sam will discuss later. Okay. If you stick a string, one of the, especially these triple quoted strings in front of your function, it becomes documentation for the function. It's always a good idea to say what your function actually does. So this feature is very nice. And then at the REPL or in a notebook, if you type a question mark, you enter the help mode and it will print the documentation for the function. So in this case, we can print the documentation for the function adder there, and that's what we get out. For some reason, the notebook always produces this when you process it with Jupyter Book, but that's not very important. If you have a one-liner function, you can miss out the function and the end. So you basically just say function and arguments equals some result there. So that's grand. So we can raise things to the power. And you'll notice in the example there that sort of analogously to using a multiplication to concatenate strings, the power operator, when executed against strings, will give you multiple copies of that string. So that's old, right? You can have anonymous functions inside of Julia, or lambdas, as they're sometimes called. The syntax is very easy. It just uses this arrow operator here. So this is the value that goes into the function is x, and the value that comes out of the function is x is greater than 2. So that's going to be a Boolean that we get back from that. So of course, defining an anonymous function and then doing nothing with it is particularly useless thing to do. But this is how we would actually use it. So we have the map function, which is built into Julia, which just takes a function and then maps it onto a set of arguments. So when we ask if x is greater than 2 for values 1 to 5, then we get this Boolean vector back. So that's a really nice, compact way of doing those kind of operations. Control flow, well, you have if then else, and it works exactly as if then else statements work in many other languages. The particular syntax in Julia is, again, it uses this end to close the if statement, but we can have if, else if, and as many else ifs as we like, and then an else right at the very end as well. So we can just run that function there and it tells us what's greater or less than. Turns out that oranges are better than apples. So apples are less than oranges. There you go. A few other things that you might see are short circuit operators. So the double ampersand is the short circuit operator. So it only executes the second statement if the first statement is true. And the double pipe is the or short circuit operator, so it only executes the second statement if the first statement is true. So that's all pretty obvious, and it can be very good to write nice compact lines of code, because for very simple cases, you don't need to use something as complicated as if, else, and end. And then the thing that you would expect to have is a ternary operator as well. And this one it's exactly the syntax that I think originated with C. Basically, you have three statements. The first one is evaluated. If it evaluates to true, then statement B is executed. And if it evaluates to false, then statement C is executed as instead. Again, very useful for writing compact code using a ternary operator. Then on to loops. So loops in Julia always go over an iterator. So that basically means you can loop over absolutely any object that has a beginning and an end. So if we loop over the numbers 1 to 4, I guess you understand that, you know, number colon number gives you all the values between the beginning and the end of that. Then you get that, so you just get the numbers 1 to 4. Looping convenience functions like enumerate and zip work as well in Julia. So enumerate basically just gives you the values and the index of the values, as in that example there. And zip iterates over multiple iterables, and it gives you back the first value of each iterable, the second value of each iterable, and it's really good when you have lists of things that you want to combine into one thing that you operate on inside of the loop. Okay. Slightly novel for Julia, I can't think of any other language that does it, is that if you have a for loop which has multiple iteration statements, you basically get the Cartesian product of those iterations there. So it's going to iterate over I and j, but it avoids us having to write the double nested for loop. So this is a nice feature inside of Julia. And then finally, while loops. So it's not going to be any surprise to you, I think, by now, what a while loop looks like inside of Julia. You have a condition, and the block inside of the while end is executed as long as that condition is true. So that's just a little countdown thing which is there. And yeah, that's at least part of the tutorial for Julia. And I think at this point, Sam, we move on to you. At least that was the plan. Oh. We're not hearing you. Still not hearing.
Yeah.
That sounded
right.
better.
Can you hear me now?
Yeah.
Is that working?
Yep. So if I stop sharing.
Yeah, is that okay? Good. Right, I will start sharing my slides. So my headphones, I was so quiet for so long, my headphones turned off, would you believe? Which is probably a lesson for all of us. Right, okay, hopefully you can see my version of basically the same slides. So yes, so Graeme took the hit of introducing the basic stuff. So I'm introducing some things that are sort of unique to Julia, or at least new in Julia that aren't perhaps as common in some other languages. So the first thing we wanted to cover is the do block syntax, which well, it also reminds me of some stuff from Haskell, but I think it's actually supposed to be more like some stuff from Python. So a lot of these things are this is sort of an optional syntax. It's just nice to have. So to remind you all, we can take a function like, for example, sort, and sort takes an optional argument, which is a function to determine how to compare the items of a list. So in this case, we're sorting this list of values via this anonymous function. And obviously that's nice. Or we could, of course, explicitly define an explicit function. These, of course, do the same thing, right? Here we have an anonymous throwaway function that doesn't persist beyond the sort, and here we have a persistent function that we probably don't care about, actually. So this is rather wasteful. However, this is kind of awkward if we want to have a special case anonymous function that is really long. It's not convenient to represent it as a lambda. So this is where do block syntax comes into play, because we might want to create a long function but not actually keep it around after the case we're using it in. So we could do this, right? If we have this one-off function that does some comparisons on returns 1 or -1, depending upon the this sign effective, well, whether x is greater than 1 or less than 0, we could write this whole function out and then apply it to a map to get this. But this is wasteful because we're never going to use this function again. So instead, Julia provides this do block syntax where effectively you miss off the function at the start of map. So map takes a function at the start. You miss off the function at the start, and instead you write after the function invocation the anonymous function that we're going to apply that is going to be the first function argument. So here we write do, and then effectively what would be the argument to the function if you're writing an anonymous function, and then the body of the function, and then end. And this does the same thing as this map here. You can see that the contents, the body is the same. And rather than writing function one-off, we just write do and then the arguments. So this feels, it is a little specialized. You only really want to do it when you have cases where you can't fit the function body into an anonymous function. But it is quite nice because a lot of the functions that support this, that effectively have a version that takes a function as its first argument, like map, are set up to clean up after the outer function runs. So, for example, open, for opening a file in Julia, has a version that opens a file and returns the file handle, and a version that takes a function as its first argument that will then apply that function to the opened file and then close and clean up the function after it completes. So that's designed for use with this do block syntax, whereby you would write effectively open some file, do the things to do to this file while it is open, end, and then things would be cleaned up afterwards. It's a bit like, those of you who are familiar with Python, which is probably all of you, it's a bit like using with blocks in Python. You get all of the cleanup and exception handling that you get in a with block, but using this syntax instead. So it's worth knowing about. You see it a lot in Julian code that is code written in a kind of to the kind of community standards of Julia. So it's worth knowing it exists. So the second thing, which is a more generically useful thing, which you see in a lot of Julia code that we want to talk about, is multiple dispatch. So as Graeme noted earlier, Julia's type system lets us specify optionally types in a lot of circumstances. So we saw optionally typing a variable, and Graeme mentioned that we can also apply types to function arguments if we want to. So for example, we could, for the first time here, define a function multiply that is explicitly defined using the type specifier syntax, that its arguments must be int 64s. So we can define this function, and if we give it some things that are in 64s, it works fine. I note if we gave it some things that were in 16s, this would also work fine, because as Graeme notes, Julia will do type promotion if it can safely. So if we passed in 16s to this, it would promote them. However, if we try to pass a floating point value to multiply, it will immediately crash, and we get this error out, and we get this method error. So this is because there is no implementation of this function called multiply that takes a float and an 64, and so Julia can't find an implementation that will work in this case. So it's also the case that even if we didn't specify types, all of those examples where Graeme was calling a generic function on various different types of arguments, each time you called the function on a particular combination of types, the JIT behind the scenes, of course, compiles a specific optimization for that combination of types, because we're compiling down to native machine code, and the machine code, you know, for concatenating two strings is rather different from the machine code for multiplying two integers. But this allows us to explicitly specialize the methods we get for any combination of types. So we can obviously add additional versions of multiply for different arguments explicitly. So we could define now a version of multiply that applies to a floating point and an integer argument. And you notice that now when we do so, Julia notes that multiply is a generic function with two methods. So the methods, of course, in this case are this first method that applies to integers and this second method that applies to a float and an int. And Julia will always pick the version of the function that matches the types of its arguments. And this is, in fact, this is multiple dispatch. It's multiple dispatch because Julia considers the types of all of its arguments. So single dispatch is what you get in languages like class specialization of methods and languages like C++, where the first argument is effectively the class type, and you can call them as, you know, object dot method. So in that case, dispatch is based only on one type, the type of the essentially this type. In Julia, dispatch is based upon all of the types of all of the arguments. So therefore, it is multiple, and this is therefore it is a kind of object orientation, except that in this case, methods are bound to all the combinations of types rather than just the first argument. As a result, this also means that you can't just type my object dot method, because that isn't enough information to dispatch the method. The method isn't really bound to an object; it's bound to the types of all of its arguments. So you just naturally just type multiply and give it arguments, and Julia will dispatch to the correct version of the function. You can, of course, always provide a generic version as a stopgap. So you could provide a generic multiply like this, and this would be called for any combination of types that are not covered by explicit specializations. So in this case, this version of multiply that subtracts 1 from the product will be called if we call multiply with an integer and a float, because int float is different, of course, from float int. So we get 1 less than what we might expect when we do this multiplication. More usefully, arguably, we can also, because Julia's type system is hierarchical, as Graeme showed you the graph of types, we can also specialize a method via a higher ordered type rather than a specific type. So we can say my func applies to things that are numbers. This function will not work with strings, but it will work. So if we give it numbers, we can call my func on 2, which is an integer, and on 2.4, which is a float, and we get the values we might expect. If we try to call it on a string, we don't get what Graeme's version of something equivalent to this does and get banana banana. Instead, we get a complaint that we're trying to call my func with a string. Strings are not a kind of number, so we can't do this. If you really wanted to be pernickety, you could specify a method that takes any for one of its type constraints. This, of course, is functionally the same as not mentioning a type constraint at all, because every type is a subtype of any. Getting more advanced, we can also, as in C++ and so on, use parameterized types. So we can not just say things that are subtypes of a supertype. We can also say express relationships, like for example, this function, my func2, takes two arguments, which both must be of the same type T, and this type T must be a subtype. So the left arrow, well, less than symbol colon is a specifier for is a subtype of. So here we're saying my func2 takes two arguments, both of which must be of the same type T because they have the same symbol, and this type T must be a kind of number. So this my func2 will work for two integers, 2 and 3, but it will not work for a float and an integer because one of the constraints is they must be of the same type. It would also not work, for example, for two strings because even though they are the same type, that type is not a kind of number. We don't cover it actually in this slide, but you can also do this. So, for example, for container types, so for example, arrays have a subtype, which is the type of the thing they contain. So you can, for example, specify a function that takes arrays of type with contents type T, where T is a number, which will let it only take arrays that contain things that are numbers, for example. So you can arbitrarily descend into the type structure. Julia functions are also, all Julia functions are technically what we describe as open. That is, they can always be extended by later packages. So as a result, for example, we can extend the plus operator. So if we define, I was trying to find an example that wasn't trivial, that was actually you might actually want to use. So if you want to, for example, add speeds relativistically, you might define a trivial struct relativistic speed that just has one component, the actual magnitude of the velocity, as a float, and then to modify built-in functions, you need to import them effectively from the module that contains them. So we need to import from base plus to modify plus, but then we can extend the plus method for two arguments that are of type relativistic speed and say that it returns a relativistic speed with addition done appropriately. And then when we call two relativistic speeds and add them, we get the answer we expect when these are added relativistically. Now, again, as with operator overloading, the equivalent thing in C++, this is, of course, has a whole bunch of footguns where you can have someone implement a really stupid implementation of plus that does something completely unnatural. So you need to bear in mind the same issues here. You should, if you're going to overload something basic like plus or multiply, make sure it does something you might expect naturally. String concatenation goes about as far as you'd want to go in terms of overloading multiplication, for example. But it is nice to have this. It's also nice to have this for more complicated functions where maybe you're loading someone else's library and it doesn't quite support an optimized version for some special case you have. You can implement a more efficient implementation for some special cases yourself without having to, alter all of their code. So finally, and I know Graeme's looking nervous at the time because we're slightly overrunning, but it's okay. The exercise is fast. Finally, the final special thing about Julia we wanted to talk about is broadcasting. So all of you probably have used NumPy, and therefore all of you will be aware of the concept of broadcasting over an array type. That is, performing an operation on the elements of an array rather than the array itself. And almost all Julia operations support a broadcasting mode, including function calls. And this is built into Julia rather than being a thing added, for example, by something like NumPy. So in almost all cases, you just need to add a period to the front of the operator to use functionality. So we're going to start with a trivial array. So this is just a very simple array to do stuff. So using dot plus, we can add 2 to all of the elements of the array. So this plus operation is distributed over the entire array, and we get indeed 2 more than each of the values in our new vector. We can also broadcast on the left and the right. So if we have myArray dot plus myArray, then indeed element-wise addition happens. These are all twice the values in this array because we're adding each value to its equivalent value across. As an aside, Julia does understand the geometry of arrays. So if we use the quote operator, which forms the transpose of an array, so these are all effectively column arrays, but my array transpose is of course a row vector. So if we do a row vector plus distributing plus over a column vector, then we of course get the Cartesian product of all the operations. We iterate effectively through the two perpendicular dimensions, one after the other, and we get a matrix which forms all of the possible combinations across all the elements. And again, because Julia supports multi-dimensional arrays of arbitrary dimensionality, we could distribute across a third dimension an array with a third dimension, and we'd get a rank 3 tensor as a result, and so on. So we can also distribute function calls over our list. So, and here we're demonstrating. So firstly, we made an aside that earlier on that the question mark operator can be used to get information about a function. And indeed, all of the built-in functions are supported in have docstrings. So if we look up the isEven function, what does it do? Well, the isEven function takes things that are numbers because again, it makes no sense to ask whether a string is even, and it returns a Boolean value. So, okay, so given we know that, let's test it out. Well, actually, these are some examples. Let's test it out. Is even on 9 and is even 10 we expect. So then we could then create a new version of a new result if we distribute with a dot function call is even over the array. This is just like essentially mapping over the array, but it is faster. Then you see that is even is applied to each of the elements of the array. Obviously, the first element is 1 and is not even, and we get a bit vector out. Also notice that Julia has appropriately changed the type of the resulting vector as a result of the broadcasting. All of these things are int64 values because the return value is an int. But because the return value of isEven is a bool, the resulting vector after the broadcasting has changed type to being a vector of bits, which is an efficient representation of binary values. So this kind of implicit iteration obviously is very powerful, and you'll recognize this from NumPy. So I wrote this example because I really like the fact that Julia's image core libraries let you represent the values of arrays as images. So I'm pulling an image core and some of the image additional library to let me display an array as an image later on. So we've got image core, which gives us some functionality. We can define a simple function, the Mandelbrot set membership function, which some of you may recognize. Effectively, this returns a value from, in this case, 0 to 255, based upon whether or not a value in the complex plane iterates to infinity or remains stable when we perform this mapping to it iteratively. We could, of course, have constrained this to only take complex values, which we probably should do, but I didn't for this example. And then we can define, again, using the fact that for distributes over the Cartesian product of multiple values, we can do a concise array comprehension to generate effectively a set of values distributed across a value of the complex set of the complex plane, where it's mapping I to the real and J to the imaginary parts, and rescaling them to get values from -2 to +2, because I happen to know that's where the Mandelbrot set looks nice. Then we have a two-dimensional array, we have a function, we can broadcast multiple function calls. So the special macro @dot essentially adds a leading dot to all of the operations in the line after it. So here, it looks like we're doing essentially 3 operations. We're calling MK on a value, dividing it by 255, and then using gray, which is a function that we get from image core that essentially maps a value to a grayscale color. But actually, the dot at adds a dot to all of these. So what we're actually doing is we're doing element-wise application of MK across all of the elements of our 2-dimensional array, rescaling element-wise all of the values by 255, and then making a new matrix of essentially pixels from each of these elements. And what we get in the end is displayed nicely in our terminal, what you should expect, the Mandelbrot set for its kind of canonical domain. It's worth noting that, as a final comment, because broadcasting is a first-class component of Julia, it isn't added by an external library. Julia can optimize chains of broadcasted functions. So the inefficient way of doing this would be to effectively iterate over all the elements broadcasting MK, and then iterate over all of the temporary array by doing the division, and then iterate over the new temporary array doing the mapping to pixels to produce a final array, and that would be inefficient in both memory and time. Instead, what Julia can do, because dot is a fundamental component of Julia, Julia will pass a chain of broadcasted operations as effectively one set of raised operations in a broadcasted domain, and it will fuse, if it can, all of the component operations into one chain of operations, which it then broadcasts in one go over the entire thing, rather than broadcasting them all one after the other. Because I kind of wanted to let you know, well, I think Jerry and I both wanted to let you know vaguely that Julia also supports code introspection. We can demonstrate that Julia knows about this by using, there's a bunch of @code_ macros that tell Julia to let you know how it interprets and what the result will be of processing a particular expression. So if we have this array and we use @code lowered, which is the highest level version of this tells us how Julia interprets this at the level of Julia effectively bytecode. On this chain of operations, you see that what we get out is a chain of operations which are all contained within these base.broadcasted kind of blocks. And then there's this weird thing which you wouldn't see in something that wasn't broadcasted called materialized. So effectively, what Julia recognizes is that these operations are all going to be broadcasted in the same domain. So it will actually fuse the plus and the multiplication and the function call into one thing, broadcast them over the array, and then materialize, effectively produce the final output once it's performed this. So this is actually very nice. You can do tests of seeing how efficient it is. It's usually very efficient. I guess because we're running short on time, I won't prevaricate, I won't talk about this, but there are the @code macros go all the way down to @code_native, which will show you the actual machine code that the JIT generates if you really want to see the machine code that Julia will generate for a given function. So finally, I should make a few notes about the Julia community. This slide actually is mostly about the Julia package management because packages are an important part of a community. So Julia community is very active. It is, of course, a little smaller than the Python C++ community at the moment. We expect that. It's still large enough and it's still well supportive. It also, I think, like a lot of newer languages, people pay attention to what other languages that are new do. As you mentioned as an aside, when installing stuff, Julia up exists because Rust, the Rust language community has Rust up, and everyone was so happy about how Rust up works that we copied it for Julia, which is good because it's a good idea. There's a lot of cross-fertilization happens as well. So firstly, I'm going to talk about packages. So an important part of any community is the packages that exist from people who've already solved problems. So Julia integrates its own package manager with a module called PKG. So if you are running a Julia REPL or in a Julia kernel in Jupyter, you can use using. Using is how we load a new library. You can use using PKG to load PKG, and then you can call pkg.add quoted name of package, and PKG will call out to the internet and fetch the package and indeed any dependencies that the package says it has, and usually precompile them as well so that they don't need to be jitted before you run them, which makes everything faster. PKG, of course, doesn't just have add, it also has build, which can redo the pre-compilation if, for example, something's changed about your environment and you need to rebuild a package. It can do update to update your packages, RM to remove a package, and there are other verbs as well. I've included some links just so you can see stuff. So packages are registered in a GitHub repo called the Julia General Registry, and there are various tools like Julia packages that let you search and find packages that solve a particular problem. So this is how you kind of use PKG in a basic way, and I didn't want to go into too much detail about how to manage a project you're developing, but PKG is actually more like Cargo for Rust if you've used Cargo. So it doesn't just manage packages for your general installation, it also manages the environment for a Julia project. So the way in which when you add a package, PKG knows what the dependencies of that package are is that there is a project.2ml file as part of the project or the package, which can also be managed by PKG, which represents all the dependencies and metadata. And if you are running a project, you can use PKG commands to tell PKG that you are now in a new project and it should manage a project.2ml file for you for that project to actually keep up to date all of the dependencies as you go and keep developing. And indeed, if you look at the Git repo for this intro, there is a project.2ml which represents the dependencies and metadata for this project, and indeed includes things like the image core libraries that I was using in the previous example. As an aside, PKG has also got its own sub-environment. So if you're in the REPL, this doesn't work in Jupyter because Jupyter works slightly differently. But if you're in the REPL, then if you just press right bracket, you switch to a PKG REPL rather than a Julia REPL, where you can just type commands directly to PKG and it will perform them. So rather than using PKG add quoted foo, if you're in the PKG environment, you can just type add space foo and it will do the same thing. This is very convenient. A lot of examples of how to start doing a thing in Julia, things start with switching to the PKG environment, type these things to actually set things up. Pressing backspace on an empty prompt in the PKG sub-environment switches back to Julia. And as an additional aside, pressing question mark in the REPL can switch you to the help sub-environment, which does the same thing as help. It lets you search for functions and stuff. If you want, as a quick thing, we don't really need to tell you how to set things up because all you already have, but iJulia is effectively the Jupyter kernel for Julia. So you can add iJulia. iJulia itself also supports launching its own notebooks. So if you load iJulia with using iJulia and then type notebook, then it will try to launch a Jupyter Notebook service for you. If you don't have a Jupyter Notebook environment set up, it will in fact prompt you to ask if you'd like you to set up a Miniconda environment for Jupyter as well. So it's actually quite convenient if you don't have Jupyter already set up. And that Miniconda version of Jupyter will have Python support built in as well. So you get Jupyter and Python for free. So finally, finishing off this set of things, getting help with Julia. Again, the best thing about a community is being able to get help. So there is a forum style home for Julia, the discourse forums. There is also multiple real-time communities. There is a Slack. And of course, because communities like to have multiple different real-time communities depending upon how much they like corporate environments, there's not just a Slack, there's also the open source friendly version hosted on Zulip. And there's also presumably the thing for people who also like to play video games on Discord. So there are multiple real-time communities. The Julia Hep um, community is currently on Slack, but of course the Zulip is also very active. I think the Discord is quieter, but the Zulip is also very active. If you would prefer to be on an open source hosted thing. And yes, finally, we should advertise ourselves. So the Julia Hep subgrouping within Julia has its own core on the internet based around this website. And indeed, there are sub-channels both on the forum, on the discourse, and also on the Slack. So you know where to get help and talk to like-minded people if you want to. And it's me finished talking. And I think, Graeme, the next plan was to go to the exercises.
Can you hear me again? Yes. Yeah, I think we should do that. I think we should make it exercises/coffee.
Yes, fair enough.
Probably.
Yeah, we should say we weren't quite sure how long this was going to run. So as always, with the first version of anything, right? Timing is a thing we work on.
I think given we have new Zoom audience, it may be time for them to see if the binder works for them. If not, take a moment to set up the environment locally for the exercise. So maybe you should go through the setting up anyway during the coffee break.
Yeah.
I mean, the first exercise is literally setting up Julia. So
yes. Yeah. So I think what we'll do is I'll probably grab a very quick cup of coffee. And then Sam and I will kind of stay in attendance so people can ask questions on Zoom. For those of you in the room, you can come and ask us here. Or as we recommended strongly, if you just take a couple of minutes to join the Julia Slack channel and look in the Julia Hep channel inside the Julia Slack community, then we can also answer questions there as well. Or if you're feeling really brave, you can unmute your microphone and speak to us. Okay, so we kind of, pause/exercises until 11 then. And the first one is to, run through installing Julia if you don't have it installed. And then the next one is actually a real kind of hands-on practical one to do a bit of numerical computing.
you will note that one was a little guided, but that's also because I had a horrible feeling we were going to have what happened, which is that we would overrun into our time. So it does walk you quite quickly through stuff, but you know, it also typing code, even if you're typing it yourself, is always helpful to pick up our language. So.
Okay, thanks. Any immediate questions or queries that people have? No, I'm not seeing anything on Zoom. So great. All right. Thanks everyone for your attention. We sort of resume the speaky bit at 11 o'clock European time. Okay, can people hear me on Zoom?
Yeah, I can hear you.
It's working well. Okay, very good. All right, so great. We thought before we started the second part of the tutorial, we would go through the quiz. So we already had a little look at how much experience people would have with Julia, which revealed that we have quite a few experts at this workshop, which is great. Okay. But, you know, quite some people who don't have so much experience, so I hope that they found the tutorial rather useful. So we thought, based on the material that we had presented, yeah, and the great thing was almost everyone had Julia installed on their laptop. We thought we would just ask some, these are like really fun, lightweight questions, so don't take them too seriously, but just a little quiz on the material that we had. The first one that we ask you is about strings, if that is a valid Julia string or not. Which poll? Which one? Oh, did you want, yeah. Do you want the QR code back? Yeah, it's also on the agenda. There's a link there. You can go for it. Okay, so the first answer is, and somebody thinks no. Someone says yes. Yes, assume that valid is a real variable. Okay, that's not the question. Okay, very good. I mean, we don't need to wait for all of the answers. The answer is no. In fact, okay, although I realize that it's a bit annoying because that is actually 2 double quotes at the beginning and 2 double quotes at the end. It doesn't come across very well in Mentimeter. It's not very clear. And that wouldn't work because it has to be a triple quoted string. So in fact, in Julia, that's an empty string followed by some characters and then another empty string. So this one wouldn't work. And even if it was single quotes, it also wouldn't work because single quotes indicate characters in Julia. So that would definitely be broken to have 4 single quotes in a row. So that one, yeah, it's not a valid Julia string, that one. You want to use triple quotes, okay? And then a little question about types. So the concrete types that we instantiate as variables, these can only be leaves of the type tree. Okay, looks like people are unequivocally saying that yes, they can only be leaves, and that is correct. Okay, concrete types can only be leaves on the type tree, so that's good. You either knew that already or you were paying attention, which I like. Okay, there's a subtle one. Okay, what's the output from running false and it's false? You type that on the command line, what would you get? Okay, nobody thinks it's the middle one.
Yeah, this,
Oh, no,
this just shows that everyone can do Boolean logic in their head, apparently. So
yeah, I think that was a quantum effect, like that interfered with the apparatus during the measurement. Okay, very good. Yeah, in fact, the first answer is correct. You would get the output false because what Julia will do is it evaluates the first statement, which is false. Then the short circuit operator kicks in and it doesn't evaluate the second statement, but the value of any statement in Julia is always produced. So you would in fact get a false. And I think that's actually given in the notebook. You can see that. Put a semicolon on the end and you wouldn't get anything. Well, you wouldn't get anything printed. Okay. So here's, if you type that in Julia, A times B for A in 1 to 3 and B in 5 to 6, what would you get? You get 6 vector elements, an array, or 5 vector elements. Sometimes you can tell how much thinking people require because the answers come in a bit more slowly. Or everyone's just desperately typing into their terminal, which is also a valid way to answer the question, is just try it. Okay, good. Well, it seems most people get the answer right. Yes, it is actually an array that you get. So when you have one of these Cartesian product operations inside an array comprehension, Julia will give you a multi-dimensional array in this case, which is actually a really nice, nice feature to have. So it's an array of 3 by 2 elements. Take it and paste it into the REPL and you'll see what you get. Yeah, that's kind of nice. All right. Why is Julia's multiple dispatch fast? Because it pre-compiles every specific type in advance, so it does all the work up front. It compiles specifically for every type when it meets it, or it compiles low-level code that works for every type. Okay, it seems that the audience's opinion is clear on this one, and it's correct. This is what it does. It compiles when it meets a set of specific type values, then you get that compiled. The first option would be terrible, because there's effectively an infinite combination of types for functions that take, you know, multiple arguments. And the third option is fantasy land, because you cannot compile fast code for that would work for all types. So yeah, okay. That's all right, yes. But leaving aside magic wand programming. Let's go there. Okay. Then what you're going to get if you do that. So we have another one of these little arrays. We know already that the array comprehension will give us a 2 by 2. But what are we going to get? We execute the bit on the end. Each element squared, or we get a 4 by 4 array because we somehow square element, or a 2 by 2 array squared. Yeah, I think everyone got that one as well. So yes, you get a 2 by 2 array, and then each individual element is squared because we use the dot hat, so the broadcast notation there. If you didn't have the dot, then you would get the last answer. So you would have an array multiplied by itself. You would just get the actual array squared, which is something that I actually really like in Julia, which is that, you know, array operations on arrays, they work as you would expect them to mathematically. Many programming languages, that really isn't the case. And that's it. Yeah, okay, so very good. Thanks everyone for participating in our little quiz. I hope you enjoyed that. I'm sure that the experts found it ludicrously trivial, but that's all okay. Now, where the hell begin to get back to Zoom to stop my, hold on. Gosh. Here we go. I will stop sharing, and then Sam's going to take over and teach you a little bit about plots. So, Sam, I'll let you take it away.
Yeah. Okay. Hi, everyone. Yes, we thought, as Graeme noted at the start of this presentation, once we've covered the basics, we should cover some things that are generally of interest to happy people, and plotting is, of course, of interest to anyone who works with data. So this is a quick run through of, well, several ways of plotting in Julia. So Julia plot ecosystem at the moment has some competition in it, which is good because it drives the major competitors to continue working on stuff, arguably. But we should say up front that you will find people who favor one over the other. So we are going to start by talking about one of the most popular plotting libraries, plots.gl. But we will mention its rival in the space later on in this presentation. Also, as an aside, if you're doing plots, you generally, especially scientific plots, you generally want to actually have nice labels and titles that use notation in them. So I should also flag that there is also latex strings, .gl, which adds a special L string, so L quoted string, format, which will pass LaTeX markup within the string. So it's nice to use, especially with plots, because it means you can express all of the plotting labels appropriately and pick up notation. So if you hadn't already, just to remind you, you would need to, using the the libraries you want to use. And of course, if you hadn't already installed them, you'd need to use pkg to add plots and latex strings to get hold of them. As an aside, plots is quite heavy, so the first time you use plots, there will be a small delay while plots precompile some stuff and set things up for the session. It isn't a long delay anymore. It used to be longer. Julia, in general, is getting faster at stuff that requires the JIT to run ahead of time. So, but there will be a couple of seconds while plots set stuff up. So, as always, we need some data to plot to play with plotting. So let's make some values from 0 to 2 pi and evaluate with broadcasting sine and cos for them. So we have some simple graphs that we can plot. So when you use plots, the basic plots function is called plot conveniently. And plot, I will say at this point, leverages multiple dispatch heavily. There are a very large number of methods implemented for the plot function. And depending on what arguments you give it, it will invoke particular behavior. So in this case, if we call plot with essentially 2 sets of coordinates, x and y, and we can give an array of values for either of them, so that plot will plot multiple figures, well, multiple plots on a single figure for each of the values. So here we're saying plot for these x values, 2 series, y and y2 as an array, a column array, and we're specifying a title optionally and some labels as latex strings for the plot, and we get what you expect. It's over the 2, we get a sin x and a cos x, and this is all nicely marked up using the latex strings. This should be familiarish to you. It's a lot like how matplotlib's plot stuff works in Python. So this is nice and easy. Plot returns a reference to the current figure so that you can modify it as well. So we're keeping it. You don't have to. If you don't keep it, then effectively you lose access to a given figure once you plot new figures. But since we have kept our plot P, we can use that to modify this plot object to add new plots on the same figures and axes. I don't think we've explicitly mentioned it at this point, but we should. The Julia convention is that a function that modifies existing state should have an exclamation mark at the end of its name. So plot here creates a new thing. It doesn't modify any existing stuff, so it doesn't have exclamation mark. But we can use plot exclamation mark to modify, in this case, the existing plot, and we're giving it a reference to the plot we want to modify in place and add stuff to it. Much like, again, matplotlib, if we don't explicitly specify the plot we want to modify, we will modify the active plot, which is almost always the last plot we created in the session. So in this case, because we only have one plot, we could just call plot and just start giving it the plot to add immediately. But to demonstrate, we can specify P, and of course what we get is a modification of the existing plot. We now have this plot of cos x squared that we produced here, rather than, as well as all the other things. I forgot to mention at this point, we can also call plot exclamation mark or plot without an exclamation mark and specify a function for the y and z ordinates of plots, and plot will call this function on the x values to generate the values of the plot for us. We don't need to evaluate the function ahead of time if we don't want to. It can be convenient in some cases if we have a very dense plot and the full matrix of values would be large. So as well as modifying whole plots by adding new plots to the set of figures, we could also specify special functions that will just modify and place a particular value for this property of this plot. So this plot has a title and has labels and so on. So we can use title exclamation mark, again exclamation mark because it modifies the plot, title to modify just the title property of this plot. And as you can see, the title has indeed changed. The layout is a little bit funky here because this back end is rendering to pings that are inline. If you rendered instead to like PDFs or EPS, the layout would be a bit better because the layout engine would be different. But you can see we just changed the title with title. We could also use plot exclamation mark title equals and just set a new title, and it would do that, but that's obviously more verbose. And if we only change the title, why not write things quickly? Obviously, so far we've just drawn line graphs. We can also specify different types of series. Plot calls these series types. So if we modify again the plot, and this is we're just omitting P in this case because it's again active plot is all we're working on, and in this type specify we want to plot y2, which was our cos plot, and this time we set the series type to scatter. Then we will get a scatter plot overlaid, in this case, over the existing curve. I was going to add some random scatter to this, but it's faster just to show you that if you can just change the series type for any given series, it's still, of course, plotting the cos underneath this. And for every type of series, there's also a specialized version of plot named for the series type. So if you wanted to just plot line plots, you could also do line rather than plot, and it would only plot line plots. If we use the scatter function instead, then we can just plot scatter plots. So if we do scatter exclamation mark, we don't need to specify the series type. And in this case, I'm also specifying some properties of the scatter plot. So it might be a bit hard for you to see on the screen, but these are little red hexagons with marker color red and marker shape hexagon, rather than the little purple circles that are the default color for the scatter series. There are, of course, as always, a number of these properties, size and so on. You can also set optionally. So that's your sort of basic 2D plot functionality. Obviously, there are more series types and more things we could cover, but we're just giving an intro. So obviously, if you're doing a publication of quality plots, you want to worry about subfigures and the layout of them, and plots does support those. There is a layout option that we can specify to plot that tells plot, if we're giving it instead of series, how to distribute the various series we're plotting. By default, of course, it puts them all on the same figure, but if we give layout a tuple, then it will distribute the series we give it across a set of figures laid out in vertical and horizontal arrangement as we specify, and it distributes the other properties as well. So here we have a plot. We have two different series, y and y2. We have a layout which says we have two vertical figures to distribute this across. And we also have two series type, a line and a histogram, which will be distributed matching appropriately. So what we get is vertically aligned a layout of the line graph we had before for series 1, and a fairly pointless histogram of where the values are concentrated for the cos function as the second series. We could also have given layout just a number. We could have said layout equals 2, in which case plot would have picked the best way of distributing two figures or two plots into one figure. We can also, however, do much more complicated things. The @layout macro takes effectively a nested 2D array and turns it into a more complicated nested layout. So this layout is effectively one column with A as a placeholder, and then a second column, which itself is a vertically divided. So this is a column vector, vertically divided into two other things, B and C. In this case, I note for at layout, A, B, and C are meaningless. They're just placeholders to indicate something goes here. So we have 1, 2, 3 spaces, subfigures, that are arranged as one full-length column, and then a column divided into two vertically. And then I'm going to define some plots, P2 and P3, which I'm saving the values of, and then I can use plot and this is another version of plot. This plot takes existing plotted figures. So P was our original plot up here, which looks like this. P2 and P3 are plots of x mapped to x squared and x mapped to x with labels. And if you give plot a set of 1, 2, 3 existing figures and a layout has 1, 2, 3 subfigures in it, then it will map them appropriately. So P, original plot, is mapped to this column, and P2 and P3 are mapped to B and C in order. So we get x squared and e to the x as the subfigures on this side. And obviously, this can be made arbitrarily complex and nested if you want to, within the limits of a reasonable figure for a publication. And you can, of course, modify all of these plots in place if you wanted to modify this this overarching plot as well by referring to P, P1, and P, P2, and P3. So this is nice. We should also mention we can do multidimensional plots, of course. So plots has a contour method and a surface method. For surface plots, it has several other three-dimensional plots. It can do 3D scatter plots if you give it 3 coordinates. And of course, you can specify these by specifying series type as well. So contour on an x and a y and a set of heights, which is just this function, and would be the same as plot x heights. Series type equals contour, as always. So we're going to get a contour plot of this product of sines and causes in 2 directions, and a surface plot of the same thing. And I'm picking here a color map so that we can see that we can specify color maps. So then if we use plot to plot these 2 figures with a layout equals 2, so we're letting plots pick how to lay out 2 figures side by side, and I'm specifying a size here to try to stop it from squashing things. Then you can see that we get side by side this contour plot of the product of a sine and a cos in 2 directions with a nice color bar, and this series plot using this pastel color scheme of basically the same function. It should be fairly clear that it's the same function as a 3D surface plot with, again, a nice color bar. So this is all quite nice. Obviously, you can extend this further. We could superimpose things on this plot if we wanted to superimpose scatters on any of these plots. We have references to them so we can modify them and superimpose other series. So this has all been done using just one plot backend for plots. So plots is actually kind of a meta library in that plots actually act as an interface to a series of backends that use different systems to render the plots. The default is called GR and it's written in Julia. But there are other plotting backends. There's one called Gaston that uses GNU plot behind the scenes to produce plots. There's one called Python plot that, as you might guess from the name, drives matplotlib behind the scenes. In general, if you want to use these non-default backends, you need to use PKG to install the relevant additional library. You get GR for free. There's also a more specialist backend, Unicode plots, which I think Graeme would agree is useful if you're in a terminal and you just want to have a quick view of a plot without needing it to be publication quality. Unicode plots renders a Unicode text encoded representation of a plot. It's actually surprisingly readable, even for 3D plots. So unfortunately, we had a technical limitation here in that JupyterBook, which generates this web page, really does not like the output of Unicode plots because Unicode plots uses terminal control codes to align things. So this is not a live demo version. This is a copy of what it produces. So to switch backends, you call a function that is the lowercase version of the name of the backend. So Unicode plots, we call Unicode plots with parentheses to call the function. To switch back to GR, we'd call lowercase gr to switch back to GR. And then if we did this plot again, which is a line and a scatter plot of 2 different functions, what we would get with a layout, bring them side by side, what we would get is something like this. This again is me copy pasting the actual output to the terminal. If it was in a terminal and it was real output, then it would actually have colored these curves blue so that you can distinguish the functions. And indeed, the terminal control codes for changing color are what really confuses JupyterBook, which is why we have this copy. But if you're doing this from the notebooks, if you uncomment the plot and run it, you will see a nicer colored, full color version of this output. So going on to advanced features, because Graeme is going to be using some advanced features when we get to talking about data frames. Plots has a lot more functionality. Firstly, plots can do animations. It can record effectively a series of frames over a set of changing values to plots, and then output them as, for example, a GIF. It has interactive options. You can get it to launch effectively a GUI that lets you interactively change bits of the plots and so on. And of course, we're all doing live plots. It can save to pings and EPS and whatever, a large variety of different file formats as well. But also of interest to us in high-energy physics and in other data-oriented disciplines, it also has an additional stats plots library, which effectively fits over the top of plots, which supports data frames and a lot of statistical plots that you might want to do with statistical data. So box plots, violin plots, various histograms. So for this, to avoid stealing Graeme's data frames thunder, I'm going to demonstrate this using the freely available data sets from the R datasets package. So there's a set of useful testing data sets that came with R, which has been repackaged for Julia as R datasets, which is nice for doing this kind of testing that things work. So first he's switching back to the GR backend so we don't get ASCII or Unicode plot versions. And we pull in stats plots and our datasets. I note that you don't need to use plots. If you're just going to do everything with stats plots, you can just do using stats plots. You don't need to have done using plots previously. So one of the things that stats plots gives us is this @df macro, which automatically essentially unpacks the provided data frame into the plot command, replacing the symbols referencing as indices. So we don't need to faff around with awkwardly accessing parts of a data frame. We can just specify the data frame's column names, and the @df macro will create a valid plot for us. So if we load the barley yield dataset, which is essentially a set of yields at various farms of barley over 2 years, and then we can use the @df macro, name of dataset, stats plots, some kind of plot, and then in this stats plots call, we are just using symbols, which start with a colon, that reference the column names, so yield, year, variety, and site. And the macro will appropriately unpack references to this data set, replacing these references in the call appropriately. So we're going to do a violin plot by site of the yields, and then group them by year so we get to see the 2 years side by side. And we're also going to do a dot plot so you can see the actual samples. And what we get is this. So as you can see, this data set has been appropriately unpacked, and we have quite a nice IM plot. It's a little blunt at the ends for my taste, but this is StatsPlot's default kernel for violin plots, and it is nicely split up as we expect. And again, Graeme will come back to this in the data frame tutorial and do some more advanced plots with StatPlots. So I promised to finish off that we would cover the alternative. So the alternative plotting framework is called Maki-e from the Japanese. We're effectively decorating things with gold because it produces beautiful plots. So Maki is newer than plots.dl, and some of the initially, if you go back only like a year or two, there were a few rough edges. It is getting less rough edges and more features as it goes on, and it has always had a slightly different philosophy than plots.gl regarding how it does plots. It has a bunch of powerful functionality that isn't in plots. So it has an OpenGL backend for 3D accelerated plot rendering. It also now has, I noticed, a ray traced backend if you want to really produce fancy 3D plots. And it also has this system using things called observables that we won't go into here that lets you effectively have live updating plot view. So you can have a plot that is linked to variables in your notebook via this observable syntax. And then when you change values, the plot will update automatically behind the scenes with a hook rather than you needing to replot, which is also nice for producing animations. It also, by default, Mackie by itself has a whole bunch of useful statistical plots that are the kind of things that stats plots gives you for plots, and a lot of nice plotting features like cross-hatching. So it's arguably, if you're happy to be a slightly more advanced user, it is easy to get more complicated but legible advanced plots for publications if you use Mackie's built-in advanced features. Again, there was a split over this. We were talking about this when we were writing this presentation. I think I'm more comfortable using Mackie for everything, although plots is easier to just go from naught to zero with. It really depends upon which feature set's more important to you as to which you should use. I'm not going to be partisan on this. So we don't have time to go into exactly how to do everything in Mackie, but as an example, that pair of laid out contour plots we did in plots would be done this way in Mackie. I'm using Cairo Mackie, which is the default Mackie. It uses the Cairo backend and not the OpenGL backend. You have to activate it. Then I create a figure with Mackie.figure, and then I create. Notice I haven't made a layout here. When I make a contour, a filled contour, I specify the figure, and I can specify, even though I haven't given this figure a layout ahead of time, I can specify every time I call one of these plotting functions a notional row and column to place this element in, and the figure will, when we render it, appropriately size all of these columns, 1, 2, 3, 4 columns, so that the resulting figure uses, of course, less space for the color bars than it does for the actual plots. Otherwise, this should be fairly familiar to you. This looks a lot like what we're doing with plots, except that we need to specify color bars separately, and color bars take a reference to the plot that they need to have a color scheme for. So finally, to quickly finish up, plots.gl has stats plots as an extension. Mackie has algebra of graphics. Algebra of graphics is an extension that, well, mostly gives you an R-star algebraic representation of plotting processes. And it also has built-in support for data frames and basically anything that is tabular data that supports a particular set of tabular data access methods that a lot of Julia libraries do. So, for example, the Julia MySQL libraries support the same backend. So, algebra of graphics can plot things from MySQL, from the MySQL database. Anyway, again, to compare things, we had up here this statistical plot with a violin plot and dot plots for this data set. The same thing in algebra of graphics to demonstrate what I mean by algebraic representation of plotting processes. Algebra of graphics essentially represents a plot as a workflow whereby there's a pipeline that we compose different operations. So we have this plot consists of a data layer where we bleed in the data from this data frame, a mapping layer combined with the overloaded multiplication operator, which maps the data values to appropriate things. So we're mapping site to X effectively and yield to Y, and then we're mapping the color to year, and we're also mapping a parameter called dodge, which is used to separate out multiple subplots from year as well. And then we combine that with an analysis layer, which in this case we're just using 2 visual analysis layers. The analysis layer can also include things like, for example, regression lines happen in the analysis layer. And here we want 2 different visual elements. So we're combining them with a plus, so we get a pair of elements at the end. So this all looks like just a mathematical algebraic operation. And then we draw the result of this, and what we get is this slightly different plot, because algebra graphics has slightly different ideas about how to present nice data, but you can see it's the same data. The plots are separate. There's 2 violin plots separated, and there were overlaid dot plots. It's picked its own color scheme, but this is effectively the same representation as this one up here. So that's everything for plots. As I said, neither of us will be sad if you pick plots or Mackie for any particular representation, but I think Graeme is going to use plots and stats plots for his data frames intro, which is next up.
Yeah, okay, thanks, Sam. Yeah, everyone has their good ideas of exactly what should look like, and can't see anything without these. And so you have many different options in Julia. And yeah, I do love Unicode plots, because when you want to just do something really fast and splurge output on the terminal, it's great. Okay, so let's go to here. And let's, oh, yeah, I'm trying to show you. Yeah. Moving that bit. Hide that. Okay. Is that looking good for everyone? Yeah? Okay, perfect. All right. So to finish off the tutorial, I mean, there were a gazillion things that we could have picked to cover in the tutorial, but we thought, you know, plots and data frames would be a nice things to cover, because data frames have become very popular as a way of looking at a lot of statistical data, but also, you know, even in high energy physics, even though our data doesn't completely naturally fit into the data frames paradigm, there are things like our data frame now and the coffee backend as well for doing high energy physics analysis. So it is certainly a paradigm for looking at data which is useful, and it does fit very well for many different things. So we thought we would run over quickly over some of the sort of key concepts of how data frames are implemented in Julia. So as ever, I mean, I just print the terminal output there for just showing you how you add data frames through the Julia package manager. So this won't be any surprise to you now. And let's get going. So what is a data frame? So a data frame is basically tabular data that you have. And to just get started, let's create a little table. So let's create a little table of leptons where we set the mass, the symbol, the charge, etc. And we just call one of the constructors for data frame here with all of those vectors. And when you print that data frame, you get something that looks exactly what you would expect. So you have columns with different names, which take different data types, and then you have rows which represent each of the individual data values in there. As you can see, you can obviously construct these things using vectors, although we also slipped in a little scalar in there, which naturally just gave you the same value right across the data frame. And there are a bunch of different ways that you can create data frames. You can create them from arrays, you can create them from tuples. So just go and have a look at the data frames documentation to work out how to do it. Okay? But usually, right. One of the most common ways that you would load data from a data frame is because data frames map basically to tables like CSV. CSV is a very common way of reading and writing tabular data. So we can use the CSV package to read in tabular data into a data frame. And for the rest of this tutorial, I'll be using the data set that was used in the Higgs machine learning challenge. So there's actually a reduced version of that data set in the tutorial website. But actually everything that we do here will work with the full data set as well. So really easy to read. You just call csv.read and you just add this extra argument telling it that you want to read a data frame, and then off it goes. And this is actually quite a big chunky data set. As you can see as I scroll along here, it has very many columns, which you can read the documentation about, but just to sort of give you some idea, the pri are like the primary variables, which are basically built from the reconstruction of the event, and the der are the derived variables, so it's some combination of things that have been pushed into a new data set. And we have in these data sets jets and leptons and taus and even subjets as well. So there's a bunch of things which are in this data set. It's probably actually was too big to put on a screen, but okay, you're just going to have to suffer it. Of course, when you read in a data set that's that big, you probably want to work out what the heck's going on. So there's a nice function just called names, and if you call that on a data frame, then it will print out the names of all of the columns that you have in the data set. If you want to know the types of the columns, you just call the L type. So that's the element type, which you can call on any collection inside of Julia, and it will tell you what the types of the columns are. So let's look at some of the basic operations that you can do on data frames. What's nice about data frames, I think, particularly in Julia, is that there's a clear consistency to the way in which data frames is implemented. So that means that for accessing data from a data frame, it's always the same kind of model, which is essentially you do a double selection over rows and columns. And there's a number of different ways that you can specify that, but that is essentially the way that you do it all the time. The template is always the same. So if you want to just extract some of the data from the data frame without copying into the rows specifier, you just put an exclamation mark. And then you list the row that you're interested in. So if I want to look at the data for the number of jets that I have in my event, then I just do it like that, exclamation mark jet number. And then I just get out this nice vector of int64s, which tells me how many jets were in each of the events. Now, there's a few other ways that you can access the data as well. So you can actually sort of directly access the column as a member of the structure, or you can use a string name for the column name as well. The way of doing it above is actually the more recommended way. It's slightly faster than the other ways, but if you have like spaces in your column name, then you might need to use one of the string representations as well. So there's a few different ways of doing it, but the one which we give here is the one that we will use consistently through the rest of the tutorial. Obviously, if I specify a row and a column, then I get just back a nice scalar that tells me what the number of events were in the sixth, number of jets were in the sixth event. And if you can also use that as an accessor. So if you modify that value, then you will actually modify the value in the data frame as well. So if I set that to 666, which I would laughingly call a diabolical number of jets, and you have a look at what the value is inside the primary data frame, then you see that this value has actually changed to 666. So data frames are mutable in general. You can modify the data as well. Just notice that there's a slight difference between calling one column name inside angled brackets, then you get back a data frame, versus calling it as a scalar, and then you get back a vector if you get multiple columns, or just a scalar if you only ask for the one column. So that's how you can access the data inside the data frame. So let's restore sanity before we go on. Set the number of jets back to 3. Perry, yeah.
Instead of using exclamation mark, not to use the colon. When you want to select all the rows,
Yes.
When you do slicing or whatever of matrices, and you put colon, you don't put exclamation mark. Why they do that here?
So I think the reason that exclamation mark is used in that one is just to remind you that you are accessing the primary data in the data frame. So it's kind of analogous to the exclamation mark on the end of a function name, meaning you could modify the data at this point. If I understand your question correctly. That is the way it is. You can argue whether it's the right way or not, but that is the way it is. Okay. And if you use a colon, you generally copy the data as well, except in that example where we were setting a particular value from in the data frame. But yeah, if you use a colon, then you copy the data. So here I'm just going to create a little mini data frame. It only has rows 1 to 5, and it only has 2 of the columns we have. And then if I set the values of the columns, I set the primary, the tau transverse momentum to this, and then I look at the data frame, sorry, the values of the data in the original data set, you can see that they have not changed. Okay, so this mini Higgs actually has different data now. It's separate, independent from the original data frame that we copied this out of. Okay, that is an example of how you can set new values for a column of data. You just pass it in a vector, and it will set the values appropriately. You can do exactly the same thing for a row as well. So if I want to set the column values for the third row, I can set it to those values there, and indeed I get this as the result. So I set, first of all, I set these things, and then I set this, and this is the result that you get. Okay. Selecting columns from a data frame is very flexible. Let me show you how to do that now. Okay, so if you use the not specifier, it will not select that particular columns that you give there. If you use calls, you get the union of all of the columns that you give. One of the really nice things is you can use a regular expression, so you can just match against the string names of the columns, or you can specify the column names as integers as well. And the order in which you give the columns is respected. So this is a nice way of reordering the columns inside your data frame as well. So if I was only interested in the primary jet variables from the data set, I can create this new data frame called Higgs jets. It selects all of the rows, but it only selects the event ID column, followed by all of the jet columns there, and you can see that I get pretty much what I would expect. So I have event IDs first, and then I have all of the jet variable columns there. So this is a nice way of working with a subset of the data. In this case, I'm copying the data, okay? So I'm not going to mess about with the primary data set. Okay, sorry, these are too big. If you just want to work with views of the data, you can do that as well. So you just use this @view macro, and then it's just going to basically give you a view which is very efficient if you need to be working with a particular selection of a very large data frame where you do not want to copy the data across. So you want to, but you want to have a sort of easier way of manipulating that particular data. So in this one, I create a view which only gives me the values for the leading jet. Okay? And just to underline the fact that it is a different object, if I look at the type of this object, it is in fact an internal type called a subdata frame, as opposed to the type of the original data frame, which is a data frame object. So this is a different kind of thing. Okay, so that's the way that I can access the data and maybe modify some of the data as well. What's nice about the way that Julia handles assignment to the data frame is it uses the same kind of broadcast operators, which will now be familiar to you from working on vectors and arrays. So if I want to set some of the data to a particular scalar value, then I use dot equals. If you use equals, it won't work because it doesn't know how to do that assignment across what's effectively a vector. So I could do that, and it gives you back what you would expect there with the dot equals. Or I can just do a dot plus equals, and then I add 10 to every one of the event IDs as well, and my little mini Higgs data set. So it's easy enough to broadcast operations along the columns of the data frame. Okay? As we sort of already saw how to change data in a data frame, we can also add new columns to a data frame, and that's really easy because the syntax is just basically take my data frame, and for this column, which didn't previously exist, set the values equal to something else. So if I wanted to give names to each one of these events, so I go from Alice through to Elmer, then I just set a new name column, giving it the appropriately length vector, and that all gets set up kind of nicely with me. Probably you'd want to do something a bit more sensible than that, but if you wanted to give your events names, then you can certainly do it. So that is for selecting, replacing, adding data. How do we do something which is more interesting? Well, the first thing that one would often want to do with a data frame is select data that passes some particular criterion. And that's really easy to do inside of Julia as well. You essentially want to make a Boolean selection against each of the rows. And the way that you do that, at least one of the ways that you can do it inside the data frames package, is by calling filter. And here the notation, you're going to find that this notation is quite consistent across data frames, because essentially the notation is a column which is then essentially piped into a function which returns a value here. So in this particular case, I'm using this lots of jets function, which will return true if the number of jets is 3 or above. Okay, so I pipe the jet number into there against Higgs jets, okay, which is this one that only has the jet variables in it. And you can see that the resulting data frame is much smaller that I get out of this. And you can also notice that I have in fact selected only the jets that had, only the events which had 3 jets inside them. So I can make selections against the data frame really easily using that notation there. Okay, of course, usually you wouldn't bother with a named function for something that was that simple. So you can very easily just use a lambda inside of here. So you just give nj maps to nj is greater than or equal to 3, and you get exactly the same thing out as we had before with the named function. Okay. And if I need to select based on multiple columns, no problem at all. I just write a lambda that takes 2 variables. So here my interesting jets are the ones that have 3, interesting events are ones that have 3 jets and above, and where the PT of the primary jet is greater than 100 GeV. So I select that, and you can see that it is indeed a more strict selection. So I only have 2,300 events now, and you can also see that the leading PT is over 100 in every single case. So it's very easy to make these multi-column specifiers based on that. Okay, and moving on. So how do we actually do something interesting with the data? So let's just use the standard Julia statistics package as well. And there's this nice function in data frames called combine, which will apply a function to a column of data in the first instance. But it's pretty much the same syntax as we saw above. So the idea is we pipe the values of the column into a function, and then if you add a second equals greater than operator, so it's sort of double redirector, then give a new column name, then this will put the output value into this column name. Okay, but you can see that we get a very different object in this case. In this case, we get a data frame which actually only has 1 value, because it's collapsed all of the rows down into 1 row, which gives you the mean value of the data frame. So the mean jet PT for our selection was 72.9 in this case. You can combine scalar and vector outputs as well, in which case data frames will do the appropriate thing to the data frame. So here I want the mean jet PT, and I also want to know how many jets I had. Okay, so I uniquely count the jet numbers as well. Okay, so I get a data frame that looks like that in the end. That probably wasn't what we wanted though, because obviously what we've calculated here is the PT of the entire sample. What we were really wanting to get was the PT based on the number of jets that we actually had in the event. And the way to do that is to use the group by function. So the group by function takes a column, and then it splits it up into sub-data frames based on the value of unique values of that column. Okay, so we use group by, and then we work out the mean, and it's going to implicitly work it out for each of the sub-data frames that we have. And in this case, what we end up with is what we really wanted, which is the value of the PT sorry, PT of all jets, actually, the all jet mean PT versus the number of jets which were in the event. Okay, so you can see that as we have more jets, the PT goes up as well. And this N row thing is just a nice counter that tells us how many events had that particular value in there. Okay, so very good. Of course, our data isn't perfect in many cases, and data frames has a really nice way of handling missing data as well. So let's see why that's useful, because if we wanted, for instance, we were doing a lot of calculations with PT squared, maybe we want to add PT squared as a new column inside of our data frame. So we can do that very easily just using the lambda function notation there, and we put that into the column PT2. So that kind of all looks very good until we realize that, oh, wait, I've got these sort of really bizarre values here in 4 and 5 and 9 that look very wrong. So what the heck was going on there? Well, what was actually going on there is that in the CSV file, this special number minus 999 is used to indicate, oh, actually, I don't have any data there. Of course, CSV has no convention for that, so they have to use this magic number there. Now, we could filter out all the unphysical values, but data frames has a nicer way of handling that by using a missing type. The first thing that we have to do, though, is call this allow missing function on the original data frame. And what that's going to do is it's going to change the column type that we have from the particular variable, you know, it's a float 64 or an int or a string. It's going to change that into a union of that type and a missing, which allows it to contain either one of those types. So it can now be a float 64 or it can be missing as well. Okay. So we do that first of all, and we're just going to take the primary jet data as well. So this is our Higgs data set where we're going to set the missing jets. Okay. Then we're going to define a function which will return missing appropriately for us. So I'm basically going to say if the value is already missing, leave it alone. But if the value is numerical and it's less than 0, then set the value to missing. Otherwise, just leave it alone. Okay. And then I call this select function on the data set, and I'm going to map the leading jet PT. I'm going to pipe it into this missing value, and then I'm going to put it back in the leading jet PT column as well. So in this case, I'm overwriting this particular column, right? Call that on the data frame, and then you can see that what happens is the places where the data was missing, which was previously indicated with a magic number, it's now properly listed as being missing. Missing has nice arithmetical properties as well, by again the operator overloading in Julia. So if you add, 1 plus missing equals missing, missing times missing equals missing. So it will handle the missing data value generally quite smoothly. So we get that there. There's one thing to note there was that there was a convenience operator that we used, which was by row, which just does the broadcasting for us of the values into the function. So let's do the same thing again. We want to calculate the PT squared of the jet, and then we actually get the values that we would expect. So as I said before, when you do arithmetic operations on a missing, then you get back a missing. So we have a nice data set where we record the PT2, but it's missing if it's not there. So that's a nice way of handling the data there. Okay, so let me go on and just sort of finish off this little bit of tutorial with visualization. So Sam already covered quite a lot of this, so nothing is going to be too surprising for you here. As Sam already alluded to here, I'm going to use plots and stat plots, but there are many different plotting options that you can adapt this to very easily. So let's just create a little subset of the data as well, which I'll call interesting jets, which are events where there is a jet and where the PT is, I think, at least 100 was what I selected. Yeah, so I want jets which are at least 100. So there's 2,000 of these events. Oh, actually, sorry, yes. Then I even filter it a little bit further because I don't want too many in the plots. So I'll just restrict this data frame to 2,000. And then I take my first plot. Again, I use this df macro that will map the column identifiers nicely into the vectors of values. So I want a scatter plot. Here I'm going to scatter plot the coordinates of the jets, so the leading jet eta and the leading jet phi, and I'm going to plot those down there, and can add labels and add all the other specifiers that Sam showed you in the earlier tutorial, and that will just work. And here you can see that, yeah, I don't have a very interesting distribution in eta and phi. Okay? One of the plots that StatPlots gives you is this nice marginal histogram plot, which is here. So this allows you to understand the data in the 2 dimensions a bit more easily. So you can see that the distribution in phi is very flat, of course, because that's sort of cylindrical around the beam axis, but the distribution in eta is quite peaked because I don't have detector at the ends. I've only got detector in the middle. So this is just what I would expect. I can also look at a histogram of the leading jet PT, which looks like that there, just by calling the histogram function. So that's quite a nice way of just very quickly visualizing the histogram. Because we've got this nice updating syntax for plots as well, very easy to plot 2 things on the one graph. So here I look at the leading jet PT and the subleading jet PT. And I can plot both those histograms together. I can use the marginal histogram again to plot the relationship between the leading jet PT and the subleading PT, so you can see what the relationship is between the 2 of them. And then just to sort of a slightly more sophisticated example, let's look at the separation between the leading and the subleading jets. So these are things that are usually produced back to back, but actually they can in certain event topologies be close together. So we would like to define a distance for the Cartesian distance between eta and phi. In this case, it's slightly trickier than you might think to do that, actually. The 2 things which are slightly tricky here are that when we calculate delta phi, we have to remember that phi wraps round on itself. So if we happen to pick jets which are just on the opposite side of where the minus pi to pi is, then we would get the wrong value. So we just have to do a tiny little bit of renormalization there to make sure that we get the right separation distance between the jets. But other than that, I mean, it's basically just the square root of the Cartesian distance. So the distance in eta and the distance in phi squared and square rooted. But here I have to use a trick, and that's because missing does not like greater than and less than. So I have to filter out the events which have missing values up front. Well, the easiest way to do it is to just filter them out up front. So I'm going to use Julia's multiple dispatch. Here comes to my rescue. And I say, if I've got 4 numbers, then I can calculate the distance, no problem at all. And I provide a fallback function, which I know in practice means that one of the values is missing. And if anything's missing, it's missing. Okay, then I don't bother calculating the distance. So this is a really nice way of writing the distance function in a way that is very generic and doing the right thing. Okay, let's run that through the system. So here, of course, we have to have 4 values that go into our function, which then doesn't fit on the screen, but you get the idea here. You just push in the 4 values there, you calculate the distance between them, and you stick this into a thing called jet distance. So we end up here with lots of missing values because many of the events in particular don't have a subleading jet. But the places where there is a subleading jet, then I get the distance nicely defined. And then we can actually look at the histogram plot. So you can see that this has very clearly got a peak around pi. So in general, these jets appear back to back from one another, but not always. Okay, so they can be separated a bit from one another. And again, we can print the marginal histogram that just kind of shows us the same thing as well, that you're often getting these jets back to back. All right. And that's it. That was all that I wanted to show you as a kind of basic introduction to data frames. And there is an exercise which is also available to you, the data frames exercise, which takes what we learned there and allows you to do some things which are a little bit more sophisticated than I showed you, but you should be able to work out how to get there. Okay. And that's it. So great. Thanks everyone for listening. Yes, it did take us longer to go through the material than we thought, but probably it would have taken us longer even if we thought it would have taken us longer. But if people want to try the exercises offline, then you can just get in touch with Sam and I if you're having any trouble, or use the Julia HEP Slack channel, and we'll try and keep an eye on that in the next couple of days and help you out with any problems that you come across, or just use the Slack to ask general questions about Julia as you continue your explorations. All right, thank you.
Many thanks, Graeme. Great.